This is lesson 30 of the Quantum Mechanics, a mini lecture series. So I left off with a simple representation of a wave, which looks something like this. Y equals a cos kx minus omega t plus phi. I'm just going to focus on this for now. Okay, let's take out the phase constant. Let's suppose that the wave initially is at the origin. Okay, starts at the very beginning. And Schrödinger had this picture in mind. So Schrödinger, if you recall, didn't like the Heisenberg approach of mathematical abstraction. He believed that an electron had a form something like this: psi x of t is equal to a cos kx minus omega t. This thing here, it's the Greek symbol psi. This is called a wave function. Okay, it's basically, so Schrödinger thought this probably represented the electron itself. Okay, it contained all the information about the electron. It's some function. The electron is some function, some thing, some quantity, some wave-like thing at some position x, at some position time. Okay, it can be represented at some position x and some position time as follows. And that's also equivalent to this. You can show this mathematically, which I'm not. It can even be represented like this. Okay, I'm going to explain how to get from here to here. Okay, so I'm going to try and derive something like this. I'll show you where this comes from. This is I'm going to start off with something called a mathematical idea called a series. Okay, a series is a sum of terms that follow a specific pattern. Okay, it involves adding up infinitely many things. Let's suppose we've got numbers here, x plus y plus z plus dot, 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 dot. Okay. Let's take the exponential function, e to the x. E stands for exponential. Okay, it's a mathematical function. That describes how a quantity changes rapidly as some input value x increases. Okay, so think of y as like an output and x as an input. Okay, when you draw a table of values, you can sketch an exponential. Okay, let's say from -1, 0 to 1. If you plug in x is -1, x is 0, x is 1 into this relation here, you can work out how to plot. And it typically looks something like this, okay? Intersects the y-axis at y equals to 1. Looks like that, okay? It's a curve. So it takes some input x and it maps it, if you wish, to some output y. So suppose x is 0. If you plug in x is equal to 0, e to the 0 is 1. If you type that into your calculator, x equals to 1. That's basically, so e is just a number. It's about 2.72 to 2 decimal places. And we can also express e to the x as an infinite series. Okay, it's basically equal to 1 plus x to the x squared over 2. This is called 2 factorial. Okay, that explanation mark, the explanation mark means factorial, just means 2 times 1, okay, plus x cubed over 3 factorial plus dot, dot, dot. Okay, so x to the 4 over 4 factorial dot, dot, dot. 3 factorials is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Okay, it's just multiplying backwards. Think of it that way. This is also known as a Taylor series. Taylor series expansion. Okay, e to the x has been expanded, if you wish, into this form, infinitely many series of terms. Okay, and the pattern here continues with each term having an exponent. Okay, an exponent means like a power that increases by 1. Okay, so 2 becomes 3, 3 becomes 4, etc., etc. And the denominator, that's the factorial of the exponent. Okay, so 2 factorial comes from the exponent 2, 3 factorial from the exponent 3, etc., etc. And so this allows us to approximate the value of e to the x for any given value of x. Okay, why? Because it's like breaking down a complex function into smaller pieces, simpler pieces. So example, 123 can be expressed as 100 plus 20 plus 3. Okay, it's just breaking it down. That's what we've done here. And I'll continue in the next video on this idea of an expansion.